Hello everyone. I thought it might be helpful to generate a video tutorial of sorts to familiarize you with the tools and features in ChemDraw and how you can employ these to learn more about a specific compound, to generate structures, mechanisms, and even predict HNMR shifts or CNMR shifts. So to begin, what I've done is I've opened ChemDraw here and I've got some things that we're going to do to familiarize everybody with the necessary tools. Typically when you open ChemDraw, the main toolbar with your bonds and your atoms and your electrons is already open, but just in case it's not there, I've made sure that it's not showing here. If it's not showing, you're going to want to go to the View tab and hit Show Main Toolbar. And then you should see something that comes up like this, either at the top or on the side of your screen, or even sometimes it floats on its own and it's not actually attached to the edges at all. Okay, that's going to be the main toolbar, that's why it's called the main toolbar, that you're going to use to generate structures and formulas. Okay, a couple of the other helpful toolbars that you might be interested in is there is a periodic table window. And on that periodic table window, you can click individual atoms. There's oxygen, and it gives you the atomic weight and some other information about these elements. Okay. Close that. Another useful tool, another useful window is this analysis window. And to show you why that's useful, I'm going to have to generate something here. And so let's just be very simple here. I'm going to do a propane. Okay. We'll come back and show a little bit more about how to make sure those bonds are connected properly. So there's propane, right? I know the chemical formula of that. The condensed formula is CH3, CH2, CH3. Okay. If I take that and select it, typically what you drew last is going to, when you hit this lasso button, is going to select it. If it doesn't, you can always just come in and actually lasso it. And so I've got my propane there now, and I go to the View, and I hit Show Analysis window. And notice it gives me the formula and the exact mass, and just a little bit more information there. And so that can be helpful for you to just do some quick calculations on the weight of your molecule and the molecular formula. Okay, delete that. Okay, so let's get started here. First, I want to show you how to generate formulas in ChemDraw. So for things like that have subscripts or superscripts, how you're going to handle that. Okay. So for our first example, we want to generate the reagents necessary for bromohydrin formation from an alkene, 1-butene in this case. Okay. If I want to make a bromohydrin, that means that I broke the pi bond and I added a bromine to one carbon. The source of that bromine would be Br2. And then to the other carbon I added an OH, and the source of that OH has to be water. Okay, so what I need to react with 1-butene to make the appropriate bromohydrin is Br2 in water. So what I'm going to do here is I'm going to click this text tool, and I'm going to come right here and click so that I have this box that tells me that I'm ready to type. I can type capital B, lowercase r, 2, comma, capital H, to capital O. And then I can come in and I can highlight the 2 and go here to text, style, subscript. And then I can highlight this other 2, come back here to text, style, and subscript. Okay. Alternatively, there are some short keys there that will turn things into subscripts and superscripts for you with just a hit of a button. But since that's different on PCs and Macs, I'm just going to leave it doing it, using the toolbar options. Okay. So there I have my Br2 and H2O. Okay. in no particular order because they're all in the same pot with the alkene. Alternatively, I can create this text box again, and I have one right here, and I can hit Control F. That's telling me that I'm going to make this a formula, or the things that I want to type need to be, are actually chemical formulas. And so then, for a Mac, it would be Command F, if I'm not mistaken. So Control F for a PC, Command F, right, before you start typing. And now when I type capital B, lowercase r2, that 2 automatically becomes a subscript. I put a comma there, capital H, 2, that 2 is automatically a subscript, and a capital O. Okay, so if you know that all components of what you're going to be typing have that formulaic design, then you can go ahead and hit Control F for a PC or Command F and have it all show up as chemical formulas. Okay. Now, in this second example, we're going to be generating 1 cyclopropyl octane. Okay, so one thing I can do is I can simply just take my solid bond here, which is only a single bond. Okay, just below it is an option for multiple bonds. Okay, but I just want my single bonds here because there's only single bonds in cyclopropyl octane. Okay, and I can have a 1. I click pretty much anywhere on the screen there and I get this bond. Okay, and then I want to make sure I come in right at the end, and I even see this blue circle here so that I know that the next bond is going to be connected properly to that previous one. So I've got 1, 2, 3, there's 4, 5, 6, 7, 8 carbons there now. Okay, and on carbon 1, I need a bond to a cyclopropyl. So I can have my bond here. Okay, it looks like I'm gonna run out of room, so I'm just gonna lasso this and scoot it down. Okay, and come back, hit my bonds again. So here was carbon 1 of my octane, right? 1, 2, 3, 4, 5, 6, 7, 8. And off of that carbon 1 is a cyclopropane. And there we go. Okay, bond angles look a little rough there. What I can do is lasso this structure and then come to structure, clean up structure, and my bond angles will be more accurate than the structure maybe I originally designed. Okay, so that's one way I could generate 1 cyclopropyl octane. Another way is if you know that you're going to have a long carbon chain, okay, you can come to this button over here that has the, it's a carbon chain with an N, and there, if you click it, what you can do is, as you start to generate your structure, right, it's going to have the number pop out there. So you just scroll over until you get to 8 carbons, and that's a guaranteed octane chain. Okay? And then I need a cyclopropyl. I could go in again with my single bonds here and generate that cyclopropyl and then clean up the structure. Alternatively, what I can do is I can add my bond. And then at the end of that bond, I come over here to my palette of cyclics. They've got all the way from cyclopropyl or cyclopropane to this cyclooctane here. And then down here are your benzene rings, or your benzene ring. Okay, so I can choose the cyclopropane, click it right there at the end of that bond, which makes it actually a cyclopropyl substituent with 1 fewer hydrogen than than propane. Okay, and so either one of these is 1 cyclopropyl octane. Okay, just generated a little bit differently using the different features on the toolbar. Another helpful tool that we have to that we can use to learn naming or to, in some cases, reinforce our understanding but we have to be very careful with this tool. I'm going to circle this. I already named this IUPAC 1 cyclopropyl octane. Okay, I lassoed this, and I come here to structure, and I'm going to ask ChemDraw to convert my structure to a name. Now, in many cases, the name that ChemDraw generates will be the name that you would generate based on the IUPAC rules you've learned in this class. However, there are some differences, and so that means that you can't exclusively rely on ChemDraw to get you the right correct names. Notice here, this calls this an octyl substituent on a cyclopropane parent, which is not the convention that we used for naming. We said you find the longest carbon chain or ring, and whichever has more carbons is your parent, okay? So yes, in some cases, and I'll keep showing you the use of this tool to generate names from structures. In some cases, it's going to match what you would do, and in other cases, it's not going to. So it's not going to be a tool that I suggest you rely on when naming things in an exam setting or in your lab reports. Okay? All right, and then I can freely kind of move this name around. If I want to delete it, I could delete it. I can undo that, Control Z, or I believe Command Z for a Mac. I'm just going to leave it there, okay? Just to show you that the ChemDraw generated name, and maybe I'll put that here now, okay? ChemDraw generated name doesn't match up with how you're expected to name this 1 cyclopropyl octane. Okay, all right. Example 3 here is a structure that has heteroatoms involved. So notice it's not just carbons and hydrogens, and also has some chiral centers that I'm going to have to include in my structure, okay? So let's just start off by building our parent chain here, and that is a heptane, right? It's actually a heptanol, but I'm going to have the 7 carbons. I'm going to go ahead and lay them down. I have a tendency to just use the click and add instead of this N. I don't know why. 2, 3, 4, 5, 6, 7. Okay. At carbon 2, I have an OH. Now here, and I'm just going to lasso this and pull it down again, give myself some room here, make sure nothing's crashing into anything else. Okay. Now here's where I want you to be careful, because you can come here and kind of hover over the end of that bond. And in this case, you would want to do this because you're changing that right now that's a carbon, right? If I leave that alone, that is a methyl group on carbon 2 there, okay? And you can kind of hover over it to change the atom. But on some versions of ChemDraw, depending on how new your laptop is and I think what program's running it, it predicts what you want as soon as you type one atom. So if I type, say, like a C for Cl here, it goes ahead and puts a Cl there, okay? But if I type, say, a B, oh, well, no, okay. Well, unfortunately, it's not doing what I thought it was going to do here. In some cases, if you're not careful with what you're trying to type here, it will change it to other things. And so my suggestion is to click this text tool and then click right there, and then you can type exactly what you want. So I want an OH group, and I know that since I got that blue circle, that it is directly attached to that at the end of that bond. Okay? At carbon 6 here, 1, 2, 3, 4, 5, 6, I have a bromo. So I got my bond there now. I'm going to come over here to this text tool, and then I'm going to click that blue circle to make sure that it's directly attached to the end of my bond, BR. Okay? Now I'll come back here just a second and show you what happens if you're not perfectly attached at the end of that bond, right? Let's say you're kind of willy-nilly here and you just type a BR there. Notice that the font is different for this BR versus this OH, and that's telling you that this BR is not actually attached on your structure, okay? Now if you get it really close, I suppose it doesn't visually matter, but in some cases, that can be the difference of you giving me a very clear, unambiguous structure, or you giving me something that results in point loss. You'd rather just be completely accurate, okay? And the way you do that is just to make sure, I'm going to delete this bromine, is just to make sure you come in here and hit that text tool, get that blue circle, and then type what you want, okay? So right now I've got a 6-bromo-heptan 2-ol, but I need a specific isomer of that of that species. I need the 2R6R, okay? And so in order for this OH carbon, the carbon 2 here to be R, I need priority 1, priority 2, priority 3. I need a clockwise rotation, right, with the lowest priority group going away from me. And so that's going to be a wedge OH, okay? I'm going to come here and notice that you have this wedged bond here. Kind of looks like a filled-in carrot, right? And I'm just going to click over the original stick bond that I had. And now that's a wedge, and it is indeed priority 1, priority 2, priority 3, looks R, is R, okay? If I want this carbon 6 to be an R orientation, then in that case I'm going to need my bromine to be on the dashed or the hash wedge, which is right here on your toolbar, okay? I'm going to click that, and then that's going to be priority 1, priority 2, priority 3, looks counterclockwise S, but my lowest priority group is actually opposite where I need it to be, so this is R, okay? If I want to confirm that, what I can do is I can grab or lasso this structure. Again, if it doesn't automatically lasso it for you, you can just come in here, grab it, structure, convert structure to name, and there I have 2R, 6R, 6-bromo-heptan 2-ol. So in this case, the naming feature of ChemDraw lines up with how we would name it according to the rules that we've learned in this class. Again, though, you have to be very careful with that because in some cases it simply won't. Okay, let's move on to this example here. Example 4 involves heteroatoms, right, because I've got a diol there. And it also involves multiple bonds, both a double bond and a triple bond here with this En double bond and Yne triple bond, okay? All right, so I have a 7-carbon chain here, right? 1, 2, 3, 4, 5, 6, 7, okay? At carbon 1, 2, 3, 4, 5, 6, I have a methyl, okay? At 5, between 5 and 6, I have a carbon-carbon double bond. 1, 2, 3, 4, 5, okay, between 5 and 6 here, I have a carbon-carbon double bond. You can do carbon-carbon double bonds one of two ways. You can hover over the original sigma bond that you have while still having clicked this single bond on your toolbar. You can hover over it till you get that blue mark and click again and you'll get a double bond, okay? I'm going to just undo that. Alternatively, what you can do is you come in here to your multiple bonds, and then you're going to have to hold onto that button to get this menu of other options and go to the double bond, because originally it had selected the triple bond for me. And I can come in here and hover and change that. Okay. At carbon 1, between 1 and 2 is a 1 triple bond, right? Okay. Now here is where you don't have the option. Notice that if I come in here and click this and I hover over here, I can get the double bond, but I can keep clicking and I'll never get a triple bond. Okay. So in order to do the triple bond, you do have to come to this other tool with all the multiple bonds, select the triple bond, and hover between carbons 1 and 2 to get that triple bond. Okay. At carbon 4, 1, 2, 3, 4, I have 2 OH groups. So I'm going to go ahead and put in the 2 bonds, and at the end I'm going to very carefully first click the text tool, then come here, say OH, click here, OH, okay? All right, now hopefully you're looking at this and are a little bit uncomfortable because my bond angles, right, particularly here for my sp carbons involved in my triple bonds, are horrid, okay? That's supposed to be linear, okay? I can fix that, right? I could grab this carbon right here and rotate it until it's nice and pretty. But notice I start kind of changing the size and messing around with it a little bit more than I necessarily wanted to. Okay, but it's fine. I can fix it like that. I'm going to undo that. Alternatively, remember, you can lasso this structure, come here to structure, the drop-down menu, and hit clean up structure, and your bond angles will be perfect. Okay. So there I have a 6-methyl hept 5 ene 1-ine 4,4-diol. That's a mouthful, right? Let's see if ChemDraw names this the same way that we would have. Okay, convert structure to name. Yep, looks like it's exact. Okay. Now the one thing I could have done here, by the way, while we're looking at it, is the only difference is that I could have also written this. Okay. Or as 6-methyl, okay, 5 heptene, because notice that in this case or this case, this 5 can only be locating the carbon-carbon double bond. Here, still the 5 can only be locating the carbon-carbon double bond because it's the next thing that you get to that you need to be locating. But everything else has to stay the same. 1-ine 4,4-diol. And that E stays there for that ine simply because it's awkward to have 2 vowels next to each other or 2 consonants next to each other. So you determine whether you're going to keep that E or not based on the fact that this is a D, which is a consonant, and so you want to break it up with that E vowel. Okay? All right. Okay, a couple more examples that I want to run through here with you. Now here, we're going to do a little bit more with our electrons and our arrows and generate the mechanism for the formation of this major alkyl halide product from the reaction of this asymmetric double bond with HCl. Okay? Now, if you're familiar, as you should be, with HCl reacting with a carbon-carbon double bond, then you know that this goes through a carbocation, where the first step of this mechanism is the pi bond opening up to form a carbon-hydrogen sigma bond, and leaving a carbocation on the more substituted carbon of the original double bond more often. Okay? So to show that electron movement, I'm going to have to make sure that any electrons I intend on moving or that are moving, that I'm showing very clearly. Okay? Since the pi bond is opening up and reaching out for the hydrogen can only accept those electrons by releasing the chlorine. And the fact that I don't have this HCl bond drawn out means that I can't fully show the mechanism on that species. Okay? So I'm just gonna come in here and make sure that I show the bond between hydrogen and chlorine. Okay. The other thing I want to do is, since it's a mechanism and since mechanisms are showing bonds breaking, bonds forming, and movement of electrons, I'm going to show all my electrons. Okay. I'm going to come in here and put in the lone pairs on this chlorine. I come over here to this tool that's chemical symbols. There's all kinds of things here. If you hold down your mouse, and you can see the other options here. You've got circled charges, you've got regular charges, you even have radical cations and radical anions, and some other things here that we don't really need. There's a radical right there. Here's our lone pair, and I'm going to come in one. I'm just going to click on that chlorine, and it should orient the 3 lone pairs appropriately for me. I don't have to do much work there to position them. Okay, if you just hover over the chlorine and click, 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 should put those lone pairs where you'd like them to be. Okay, now I need a curved arrow to show this pi bond forming the bond of this hydrogen. Okay, I'm going to come over here to my arrows menu item. Okay, and right now it's got reaction arrows because it's the last thing I used actually to generate this arrow right here. Okay. I'm going to come here and click on my mouse and hold it down, and that gives me a wide array of different types of arrows. Here's the ones that you see typically in reactions. These are synthesis arrows. Down here you've got your acid-base equilibrium arrows. Here are your resonance arrows. Okay? And then over here are our mechanistic curved arrows. Okay? Notice that that you have an array of ones going in the clockwise direction, and they change in how much they arch, and so you might have to make some choices about how far apart your starting materials are, and which one you want to choose. You might have to go back and change that option. Then you have the counterclockwise arrows in the same kind of very curved to not so curved. Then just below it, I'm not sure if you can tell, but these that I've just, in this top row and this second row, are double-headed arrows for 2 electron movements, as our polar reactions are. These are one-headed arrows, so the type that we might have used in a mass spec, or when we get to a later chapter and do radical reactions. Okay? I'm going to go ahead and pick this third one, okay? And I'm going to start at the nucleophile. I'm going to start at the pair of electrons that's moving, and I'm going to take that arrow to point exactly at the atom that I'm making that bond to. Unambiguous electron movement there. Okay? I'm just going to move that a little bit. So that, okay? If you don't like the curvature of that one, you can come back in here and choose one that's going in the, counterclockwise direction if you'd like it to come this way. It really doesn't matter. I need to be showing the tail unambiguously at the pi bond and the head unambiguously at that hydrogen. Okay? If that hydrogen's going to accept those electrons, then clearly it making only one bond, right, has to release these electrons to form a chloride. Okay? Notice that this bond right? And where the electrons are going is a much shorter distance than what I had here. So I'm probably going to need a more curved arrow, okay? And this is just, kind of intuition here. I'm going to start my tail here and push up around to the chlorine, so that's going to be a counterclockwise motion, okay? Of course, if you put down an arrow and it doesn't look right, you just go in and find a different one. I'm just thinking ahead here, okay? I want the counterclockwise one, and I want a little bit more curve to it, okay, to make sure that I can start my tail right here and unambiguously point at the chlorine to receive those electrons. Both of them, so I used a two-headed arrow. Okay, good. Now that's the first. Both of those arrows, both of those electron movements comprise one step of this HCl addition to an alkene. So now I'm ready to show that I'm moving to another step, okay? And in this case, I end up with my carbocation intermediate and my halide intermediate, in this case, the chloride, okay? So I'm going to build my carbocation structure, which means I preserve all of my sigma bonds. I'm not breaking any sigma bonds with HCl. Well, not any sigma bonds on my organic carbon species, right? I've made a hydrogen-carbon bond between the less substituted carbon and the more, and the hydrogen. And I've got a carbocation forming preferentially at my most substituted carbon. So I come back here to chemical symbols, I find my carbocation, and I make sure that I place it somewhere that is clearly associated with the carbon that it's meant to be associated with. If you prefer, you can use the circle charge. I tend not to. It's just a preference. Okay? Now, if you don't like it over there in that corner, you can put it down here, right? Put it over here. All of that's fine because it is clearly, unambiguously associated with that carbon. If you don't like how teeny it is, you can highlight it, right? I click on it, and then notice that my arrow starts changing in size, and I can kind of fluctuate the size of that carbocation if I'd like, make him big, move him back down here, okay? As long as it is unambiguously associated with this carbon, then you're fine. You start putting it somewhere right there, that doesn't mean anything to me. Or that doesn't mean anything specific, it doesn't mean what you want it to mean. Okay, let's put that right back there. I'm okay with that. And then I also have a chloride, okay? That's just a Cl. I use my text tool to generate that Cl. I come back in, get my lone pairs, and I'm going to click 4 around here. 1, 2, 3, 4. Gives them to me exactly where I like them. And then I can't forget that a chlorine with 8 electrons around it is a chloride anion. So I come here and I associate that negative charge clearly with that chlorine, or that chloride, okay? And now I need an arrow that is going to allow me to show the attack of a pair of electrons from the chloride nucleophile plugging in to that open orbital of that carbocation. So I come here, okay? I'm going to choose a counterclockwise arrow because I'm going to start over here and move to over here, okay? And I probably want a little bit of a curve to it. I'll come back and check it in a second. Let's just come here and dump those electrons right into that carbon, okay? If you think that's a little too curved, you undo that. You come here, you grab the less curved one. Maybe that one's a little bit better. Talking preference here, right? I do like that a little bit better, so I'm going to leave that alone. And then I'm going to come in here and do, that was the second and final step of this reaction leading to this product. Okay. All right. Last but not least, I want to show you another tool, kind of like the naming tool. It can help you when you're prepping, when you're writing lab reports, even when you're studying, but you want to be very careful about how much you rely on this tool in an exam setting, okay? You can predict 1H NMR shifts and also C13 NMR shifts of molecules, and ChemDraw does a pretty good job. Occasionally, your splitting patterns are a little bit different than they would be if you actually ran the NMR. Occasionally, even maybe rarely, I should say, the shifts are off, but for the most part, ChemDraw does a really good job of predicting HNMRs and CNMRs, okay? And I want to show you how to access that tool and use it, okay? So let's think about 5-methyl-1-pentyne or 5-methyl-pent-1-ine. All right, I'm going to go ahead and start with my triple bond here between carbons 1 and 2. And then I come here, there's 2 to 3, 3 to 4, 4 to 5. And then at 1, 2, 3, 4, 1, 2, 3, 4. Okay, I apologize. I named this incorrectly. This should be a 4-methyl. Okay, because if it was at 5, then actually that's just a hexyne, isn't it? Okay, that should be a 4-methyl. I apologize. 1, 2, 3, 4 methyl. All right, if I look at that, you should be comfortable telling me how many unique HNMR signals you expect. You should be comfortable predicting which one's going to be the most shifted, which are going to be the least, integrations and splitting patterns. Okay, I see one. There's a hydrogen here on this terminal alkyne. No hydrogens here. 2 hydrogens here, right? That make the same signal. 1, 2, 3, 4 unique hydrogen signals is what I predict. I predict the one that's bonded to the carbon of the triple bond to be the most shifted. Okay, I expect these methyl hydrogens to be split only by this methine CH neighbor, okay, into a pure doublet. I expect this CH right here, this hydrogen at this carbon, to be split into a multiplet because it's split by these 6 equivalent hydrogens into a septet, but it's also split separately by these 2 neighbor hydrogens into a triplet of septets. Okay, so this is the kind of predictions that we made, I think, in the forward direction, and now you're at a point where you should be able to look at an HNMR and get to a structure like this. Okay, typically with an IR's help. Okay, we're going to lasso this structure. I'm going to go to structure and I'm going to go to predict 1H NMR shifts. Okay, notice that here you're given 4 different chemical shifts. It even tells you which ones it knows are pretty accurate and which ones it's kind of maybe not so locked in at the exact number. Okay, and it shows you kind of the splitting patterns that we are expecting here for these 6 hydrogen signal right here. It is indeed a nice little doublet there. For this 1 hydrogen, right, you've got much more going on there because it's split by these as well as by these. Okay. All right. So you can see some of, you can use this tool to predict your 1H NMR shifts and your CNMR shifts. Okay, but for in an exam setting, I want you to be really careful with that because you're not going to have the time to just predict HNMR shifts of all the isomers that match whatever molecular formula or chemical formula that you get. Okay, so you're going to have to be really confident in putting things together. Sure, if at the end of the day you build a structure, you want to check if the HNMR matches. If you have the time, you should do it. But you're not going to be able to use this tool to your advantage to get you an answer for generating structures from HNMRs or CNMRs if you're not already comfortable doing that on your own without this program, okay? Because it's just a time sink to have to go through all of those things. But I want you to know that that feature is there, and you can use it as you're practicing to check yourself with some, how many unique signals do I expect for this? If you get it wrong, you can build that thing in ChemDraw and have it show you exactly where those unique signals are and maybe help you see where you went wrong. Okay? I think those, maybe there was a little bit of extra information there. I think that's a good overview of all the features that you would maybe want to employ while you're studying. And definitely we covered all the features that are necessary to know about to build a structure should we employ ChemDraw in any of your future exams. Okay, I hope this was helpful. There's also a ChemDraw practice assignment on Gradescope that's available to you through Monday, November 9th. Yeah. And so, I hope this was helpful.